would come and do a small presentation on automation grounding and the work that I've done to try to solve a lot of the problems companies have. The biggest problem we have with grounding is a lack of understanding of the very basics and the essentials when it comes to grounding automation. Now, myself and a few of my colleagues are in the room with me now. We struggle constantly with the concept that grounding is not being done properly, and probably not being done properly from the design phase, and that's where we want to grab it. Now, my company, Elite Welding Solutions, does the engineering side of it. We go and try to help when the problems happen. And usually we don't know the problems there until the line's been up and running for a little while, and that's when we really start to see the problems. The first 6 months of a line starting is a real learning curve for the real experienced people, because the line now is now telling us different things. It's starting to give us little arcing on pins and things like that. That's where the experience comes in, where we have to be able to identify what's going on. So we're going to go through grounding, the concepts of grounding. We're going to go through what the problems are, and I got a little agenda we can start by looking at. We're going to talk about why is grounding such a challenge when it comes to automation. We're going to talk about some very basic electrical terms, like the terms that I'm going to use because we're talking about different types of leads and so forth. The concept of resistance. You're going to get a tiny little bit of a resistance welding lesson. A little bit about electrodes, a little bit about time, a little bit about and how heat comes about. Talk about the 4 essentials of grounding. Now, this is actually straight out of the article, and you're welcome to get a copy of that. I actually have some extra copies of it that I could send you. And we're going to talk the things you have to look at, the things that every integrator should be doing when they're looking at what type of ground. And not just the integrator. Integrators are often taking the cues exactly from the people who are telling them, we want this stuff in our building. And one of my goals is actually to put us in a position where we take a little bit more of a lead time on that, and they get the people involved that know more about it from the design phase. Problem, of course, being the design phase is very secretive. Everybody's probably holding their cards close to their chest, and this is what we're going to do very quietly to figure out what our prices are. Different types of grounds and their effectiveness is where the whole thing kind of comes together. I'll explain to you a little bit, about the comparisons of the different places, and then we'll just have a few questions if you have any. I've got a few things here we can have a look at when it comes to applications of grounding. Now, it all kind of starts off with this. Now, I am not an engineer. I'm a fitter welder, a structural steel plate fitter, and a pipe fitter. I have my inspection papers for steel and aluminum and things, and I've had lots and lots of tickets through the years. Been great. It's been great. I've had the experience of working in nuclear. I've had the experience of working in automotive. I've had some great people and made some very good friends, and fine. But it all started for me right here. So when I did this, I worked with one of these for 18 years before I ever saw an automated cell, ever. And I thought to myself, what is the disconnect? Because I went from an industry where if you were working and you had a part and it was being grounded like that, and it was arcing, your partner come up and slapped you on the shoulder and said, stop, whoa, 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 you got some arcing over here. They recognize that arcing represents a problem with my arc. If I have a WPS and it tells me I'm welding at this particular specification, if I've got a hot ground over here and it's arcing all over the place, can you say that I'm getting the 125 amps that my WPS is saying? Probably not. So we recognized, and we would always keep our ground. It was one of the things about my apprenticeship was to make sure my ground clamp was good. So understanding that I can probably ground most things better with one of these for about $6, but automation grounding is different. It needs to be put in a certain place. It needs to be a certain, and every single time it has to be consistent. This is where the wheels kind of fell off the wagon over the years. Because we began putting grounds in place because not understanding the concepts of grounding and that the force and the pressure that we push against these parts has a vast influence over its longevity, over its performance, over the arc marks it leaves on the job. We're working with boron steels now sometimes. When you take a part and you put an arc mark on it, and you take that and you start vibrating it, or you put it through a defiance test, it'll start to crack in that spot. It's not protected. It's an arc. So we want to do what we can to make sure that that's not happening. Here's a typical, what I call a static ground. Static meaning it's holding still. And this is happening a lot, where people are saying, I have a place that I want to just stick this part in place, and I just need to get electricity to it. The concept, the whole idea behind this time, that what I'm going to be telling you here, is these aren't acceptable. They'll get you by. But every single minute that goes by is going to give, I'm going to show you lots of pictures like this, of static, where you have something that's actually depleting its performance every single minute. Every time it does a weld, it's getting less and less and less. Then somebody comes along and says, and if you're not from automotive, we look at a piece of paper that gives us cross sections, and we go, cross section says, oh, not enough heat in this one. They'll go over and they'll make adjustments to heat, make sure, because we get the bad sheets every day to tell us which ones have got to be dealt with. The problem with that is, did anybody look at the ground to find out it's the ground that's part of the problem here? Then somebody cleans the ground, next thing you know, we're getting burn through. Well, where'd the burn through come from? Nobody knows. It's because somebody actually did some maintenance. So I always strive to try to figure out a way, and I have been trying to strive to figure out a way where I can find some consistency, because it would really help me in my service to try to help cells that are currently running and not giving us a good ground. So some of the quick terms that you'll hear, and it's actually find these through that course that I said, but I got a little AC power source here, because I talk about primary and secondary current a lot when I'm talking. And that's why I kind of threw this up here, because the primary is the voltage in, high voltage, low current. We get some magnetism going, we end up with a secondary coil where we have high current, low voltage. This is your basic transformer. This is your basic step-down transformer where the voltage goes down, the current goes up. So you'll hear me talk about primary and secondary coil over the next little while. And this is how we can make a deliberate short circuit and not blow the breaker panel right off the wall. Because there's no physical connection between what we do. It doesn't matter whether you're talking about an inverter or a constant voltage power source. It doesn't make any difference which one it is. We're still talking about something that has some form of a transformer in it. Does anybody, I was about to say if anybody's old enough, but I know. With the crank on top of the welding machine, remember those? You can still buy them like that, right? All that is one piece of the transformer is going inside the other. That's all it does is transfer that, and that's what tells, what's that? Still what? Yeah. They worked really good, right? They were indestructible. Those little we used to call them tombstones, the little Lincolns too. They just go forever. So a couple of things when it comes to cabling, because I'm always concerned about cabling. How hot does a cable get? How long is the cable? Cabling, when it gets to a certain, your welding cables, when they get to a certain length, if you look under CSA W117, the Canadian Standards Association actually give ratings for how long you can travel at what current. And it's all great information. It's actually in 117.2. I've got a copy of it if anybody wanted to email me. Get my card at the end if you want my email address, and I could send you stuff. So I have different types of leads when it comes to gas metal, because we got to get up to the brain, right? So we got lead 1 that's going to take us to this point. Lead 2 will take us usually to here, and then we've got a bundle and a whip. And then we usually have, not always, and there's somebody in this room that's going to appreciate this, but there's also a bond. Sometimes we need to bond the body of a welding machine because you're having I/O issues. When you have control issues, and sometimes it'll start giving us problems. Now, I worked at one particular place named Deco Automotive one time, and we were putting in TIG welders. And we could not, the noise, there's high frequency that actually runs superimposed behind TIG welders on AC. They had to weld aluminum. And that noise was causing us so much problem that I had to body ground and drive 6-foot rods of copper into for every single welding machine, just to make it so. One particular guy named Kevin Johnson used to walk into my desk, and he was stacking up all the I/O boards that were burning out as a result of this. And every day he'd say, leave that there. Next day he'd bring the next one just to remind me there was a pile of them coming, and they were $3,600 a piece. But sometimes we find we're giving problems with communications with a welding machine. And because welding machines are getting far more sensitive when it comes to communications, we have to ground the body. Now you'll find information for that in any of the books. Lincoln, Miller, everybody shows you how to body ground if you should ever have a problem like that. Of course, we have our weld or work or ground and the connection on top. Electrical resistance is something that we create. We create it by how hard we push on something. Now, what we found out very, very early, and what everybody, when you're starting to play around with projection welds, is I can't just push as hard as I can. I don't want to push this part down. I've got a part here that I'm going to push on. So when we get to resistance welding, it's all about a part that comes into place and pressure. And that pressure builds. And as the pressure gets a chance to build, we wait until the pressure is just the right place. And then we apply current to it to make the weld. Now, how fast it gets there is not important. But what does matter is we don't push too hard, but we don't push too softly. We have to find just the right place. And now, if I want to use that pressure and that force and follow through to manipulate the resistance, that's how I make a weld. But if I walked over to this and I cranked this right up and made it a lot more, we could never get anything going here. We would conduct instead of have resistance. We make resistance. That's why the best material in the world to resistance weld is stainless, because it's highly resistant. It loves to, for a whole bunch of reasons. The nickel likes to resist, and it actually likes to hold heat and keep it longer. So this is the challenge when we don't push hard enough. This is a challenge when we don't apply pressure to a surface, to our ground, to make sure we have a complete circuit. So this is your typical, and I'm just explaining the projection weld process. Look, because you can see where the idea came from for me, because it was lessons from this that said, I think there's a better way. This is the pathway I went down. Now, these are projections. They're points. Almost always 3. And if you go to people that projection weld professionally, like Centerline, the engineer will first thing he's going to do is tell you, your projection's got 4 points, make it 3. Because a three-legged stool will always sit flat. You'll always get a good concentration of power, evenly distributed. As long as you're pushing from the center, you'll always get the same amount of pressure on all 3 points. So it can't be like the proverbial table or chair that's rocking with one short leg. You'll always get it like that. And then we've got other challenges in automotive, especially when you're trying to ground in the same place on a stamping. Where stamping's, the parts coming up, the stamping's coming up and down, there's changes. There's changes in the thickness of the zinc. There's tolerances in the sheet thickness. There's all these different things that could make it a little bit different. All along, I'm trying to figure out, well, we're able to do it here because we use 3 points and we have these projections that we use. So I knew there was an answer in here somewhere. So it doesn't matter inside of a welding circuit, and this is a very rare picture. I've never seen it anywhere else. This was a job I worked on, and I got halfway down the road, and I had a call. I had a call from the company I was just at, and they said, hey, Bob, something's wrong with this thing, and that emergency light's on. And I said, light? What light? And they said, the light up on the feeder. As soon as he said the feeder, I almost rolled the truck. It was like, oh, okay, turn around, get back there, what's going on? And that's a bolt that holds this whole assembly on. This is actually aluminum that's starting to melt from the die cast. So all that had happened in there was the bolt had come loose. It had lost its force. It had lost its ability to conduct very well just because it didn't have everything it needed. It didn't have the force that it needed. So of course it got hot, and being aluminum, and being the fact that aluminum is going to melt out at like 1200 degrees Fahrenheit, it became soft, loosened up even more, and everything just started to glow. So it was running pretty good. We were running about 600 inches a minute when I walked up to it and said, okay, now just turn everything off real slow. Just let it cool down, and it should be fine. But as I say, a very rare picture. FLIR cameras. I can't speak enough about these FLIR cameras to identify problems for preventative maintenance or anything. I use mine constantly. And looking for hot spots in cables, there's no better way to kind of do surveys on welding cells. That's why I'm not a big fan of welding cells that have cables built into cable trays on the ground. I'd rather see a cable tray that's isolated up on top so I can take my FLIR camera and I can walk right around it, because I can find the hot cable. And the hot cable is not necessarily because it's too long, because it could be too long for its diameter. There's a whole bunch of reasons you could have a hot cable. The hot cable might be there because somewhere down the line there's arcing, and copper loves to conduct that heat. So with the FLIR camera, you can actually look at things and follow them along and find out exactly where that is. And you can do it while the cells are running. And that should be the case, because the way I want to see it while it's hot. So if preventative maintenance is thought about when all this stuff is put together, it makes everything run a lot better. Because copper goes bad Copper, especially copper exposed to oxygen. Copper exposed to oxygen, when it gets really hot, gets a gray flake on it. Everybody's kind of seen it when something's fallen apart. That gray flake is the copper oxidizing with the oxygen in the air. There's 21% oxygen, 78% nitrogen in our atmosphere, and 1% argon. So it's exactly what we want it to be, but it causes all this flaking. When I'm going through a plant, if I don't have my FLIR camera with me, I keep emery paper in my pocket, and I shine up all the fittings. So if I come back the next day and that place that was nice and bright and coppery, and now it's all dark, I know that got probably over 400 or 500 degrees, because that's when it starts to oxidize and show me all the color problems. The challenges. What are all the things that are in front of us that's a real problem? So there's a typical pad. We've all seen these copper blocks that you can buy and stick them in place. This particular one was mounted in the worst possible way. It was mounted just sitting like this. Now, what makes that the worst way? It's because it's an automated cell. The end effector on the robot has come in and put a part there. It's moved away. The welding machines, the robots have moved in to do the welding. Then it comes back to pick this part up when it's done. Clamps open up, here it comes. As soon as it picks it up, it drops all kinds of junk all over that flat surface. And then along comes the next part, bash, hammers it down, hammers it into the copper. It gets really bad. It gets to the point where the copper, and I'm going to show you a picture soon, and there's actually a space, daylight, between the ground and all these bits and the copper that we need. And what's always troubled me is if somebody had those cross sections again and they saw that situation where, I don't know why, there's definitely not enough heat here, because I got a crappy leg length on one side and hardly any on the other. Well, I don't know where all the heat got to, so I'll turn these up. But they'll never think for a second to go and make sure the ground's clean first. I don't know how many times I've said to people, I said, listen, I've seen this before. Let's go clean your grounds. Grounds? Where are they? Do you know where they are? No. Now, when you took the part out, you could see it. I said, well, that's a ground right there. Is that what that is? I said, well, you really should look after that. You should give it a little shine, a little polish, do something, scrape it, whatever you do, but it's going to require maintenance. This is the other problem with zinc coating. Anybody in automotive recognizes that the zinc coating itself is very inconsistent in thickness. But if there's any arcing around it, it melts. Zinc only melts at about 700 degrees Fahrenheit. It doesn't take much to melt zinc. It melts way quicker than the steel that's going to melt at 2,900 Fahrenheit. So any type of arcing that happens in between this is actually going to start to get these balls to get bigger and bigger. They'll actually liquefy. If there's any arcing, it'll liquefy the zinc. Makes the ground even worse. So there's a deployed ground. Right? I didn't even have to work hard to make that one, unfortunately. I didn't even have to work at it. But that ground was sitting on there with 25 pounds total force. Lots of pressure. Plenty of pressure. But there was so much buildup from all this debris and everything had fallen over it. And that's a real problem. That was the one that was driving me the craziest. Because everybody would like to be able to put their cylinders, and I got one right here. And everybody would like to take their cylinders, put their cylinders so their cylinders come straight up, and make connection with the part. It sounds fine. I'm not thrilled about it that way, personally, because I don't want to push it up out of the fitting. We got to be very respectful of dimensional controls. And if I clamp it all up and then I come up and push something up, I could be causing a problem with that. So I love horizontal. I love actually pushing it sideways. I'll show you a great Welker cylinder for doing that soon. There's so many various ways of seeing a ground. As soon as I see a ground, the whole thing, how hard is it pushing on it? Is it clean? How hard is it pushing? That's the only thing I'm thinking of. I don't even know how to describe this picture. But if you see arcing anywhere in these fixtures, in a welding fixture, it should be a major, major alert. Right? This particular one had arcing all over the place, and this happened to be boron. So all the arcing was in the actual connection end of this member. So they were deeply concerned. They called me because they were deeply concerned about how do we get rid of all these arc marks? I said, well, first thing you got to do is stop. If you're going to have any arc marks, please, if you're going to ground anywhere, don't ground it in a place that I'd want to see the stress analysis on the part. At least I want to have that in my pocket. If I can put it in a place where the part's in the least amount of stress in that type of a zone, at least we've got that, a little bit of that. I'm certainly not going to put an arc mark or potential to put an arc mark in a place where it could, it's under a high stress area or vibratory. Magnetism. This is the hidden one. The real smart welding people understand that magnetism is really hurting us if we're not careful about how we do things. When you run a DC current through anything, you make a magnet. Do you remember doing that with a 9-volt battery where you do the 2 poles and you put it around a nail and, oh, well, look at that, it's just, well, we don't get that luxury because we're doing it with hundreds of amps and a lot of voltage. So when you do that and you just ground anywhere you want, you're magnetizing your entire fixture. I go to the dollar store and I grab a handful of dollar store magnets, or dollar store compasses, and I check them, kind of. They're only so good, But I make sure that they kind of work. And I'll say to a guy, they'll say, well, you're magnetized like crazy. Well, how do you know that? And I said, well, here's what we'll do. And I'll mark a spot out on the fixture. I'll take a spot that's centrally located, stick it there, put a circle around it, put a little arrow to say that's north. And I said, next time it happens, take this from me. I'll give it to him. And I'll say, next time it happens, take this and put it on there, and then text me and tell me what happens. And I had one guy text me, he said, it looks like the Bermuda Triangle. It's just spinning on one spot. He says, it's actually starting to move a little bit. And I said, you've got a magnetism issue. Now, here's the problem with that. The next time, I always tell everybody, don't believe a word I say. Try something. Next time you think to yourself, I want to see, I don't know if Bob's right about that, how it's going to affect that. Try just take a little couple of plates like this and put a weld across it and put a rare earth magnet on the other side. Just watch. Because what it'll do is it'll actually, especially with gas metal process, it'll push the wire off one side. I don't know how many robot techs I've talked to over the years, and I'm a mediocre robot guy at best, but even the guys that do it all the time, they've said, okay, we got welds off location. Okay, so you go in and you look, and I get a call and they say, does that look okay to you? I said, it looks exactly right. And they said, but the weld's way over here, and we got the part in our hands. We know it's off location. And I'll say, well, what did it look like? And very few people who do a lot of robotic work carry a little shield in their back pocket so they can watch it. And I'll say, how did it look? And of course, almost everybody says, oh, I didn't look. I didn't look at it. I just and checked it out, and it looked, it was okay. But I'll ask them, say, well, when you look at it, next time it happens, run one right away quick and see if you get a whole bunch of plasma, because that's what we're generating here, right? We're ionizing that argon, carbon dioxide, sometimes oxygen, and it's coming off one side of the wire. So even though the wire looks like it's the right place, it's the magnetism that forces it off to one side. Now, welding people that walk around with that clamp, they know this. We know. I've struck an arc many times and went, nope, that's not the spot. I've moved it into another one. We learn really quick when we're struggling with something. And often the magnetism gets so bad, and you might ask yourself, why would they even make a 7018 for AC? They have to make it for us pipe guys. The pipe guys who are welding an AC just to keep this great big vessel from being so magnetized. I've seen screwdrivers stuck to the side of it. It's so magnetized. We go home, we only run 2 shifts, because the third shift, we wrap a cable around it and run AC on it all night just to give it a different feel, to break it up so we can weld decent the next day. Right? When things get thick enough, the thicker they are, the worse it is. The nice part about automotive is, if we do it right, if we put the ground where it's supposed to be, the magnetism is going to leave us. It's not going to become part of the job. If it's isolated, if it has all the correct properties that we'll get to, it works out very well. Anything we do build up. So this is kind of in accordance, and this is how I broke it down for the article. But this is the criteria I was shooting for. Predictability. I want the same micro-ohm reading in operation from the start of the shift to the end of the shift. I don't want any changes. This was already a big thought. And these were the people that understood grounding that were challenging me. They were saying to me, we got to figure out a way. So I wanted to make something that was predictable. Inspectable. How do we see it? Can we see it? If it's inspectable, then we can define whether or not we need to fix it or before we make any parameter changes. Is it serviceable? Whoops, that's a mess. It's burned, it's this, it's that. Let's replace it quick. Something that went sitting in the crib right now. No machine shop, no nonsense like that. And of course, the applied location and load. Where am I putting it and how hard am I pushing? What am I pushing with? There's various methods available. So, as for predictability, these were the mandates that people were throwing at me. I want to compensate for changes in my stamping. My brain immediately went 1 point, bam, right? Like, that's what I'm going to do. I'm just going to hit with 1 point. Then I found out that 1 point kind of bit me in the butt. When it got a little bit dirty, a couple of times it actually fused itself because of the galvanized. It fused itself to the galvanized. I had a little bit of a problem with the galvanized, so I thought, okay, that's just a little bit too much current with the galvanizing, a little bit too much current to be pushing through a single point. Even though a single point with a bullnose on it could have done the job, that would, but when it's got to do it 500 times in a shift, it's a different story. It can't lose its conductivity during production. Yeah, okay, I get that. We want it to be the same. Because I want to avoid the robot techs having any problems whatsoever. They should. I'd love to have it, and if we get our way, it'll be in such a way they don't have to worry about that part of it. They don't have to worry about whether the ground's good or not. Because if I meet this, they'll be fine. And it gets more and more of a challenge when we talk about the different surface conditions, but we're going to get to those in a minute. Inspectability. Now, I've only ever seen it once, but one company actually had a button. They put in a button on the fixture for the robot check to push a button and retract the ground. So even though it was pressurized, they got the part in there, they're in there doing their teaching, they could push a button and retract the ground just to see the condition of the ground. And I was so taken by this because they actually looked at the ground. Because it doesn't happen very often. Most people are just making those changes and not concerning themselves with that. So it does happen. But we need to be able to get a real good look at them too. Some of them are pretty hidden, much more of a challenge. Serviceability. I need to be able to change that ground and have a fresh ground and have everything running in. If everybody here has ran around automotive, you know it. It's got to happen now, and it's got to be in the crib, and it's got to be, I need 50 more, put them in the crib. They always have to be there. So I never wanted to try to figure out something that reinvent that wheel to say we need all kinds of deployment different. I want to make it simple, and in most cases, it is okay, what we have out there. Applied location. If somebody gave me this, right here, and somebody said, got a weld on this table, where are you going to put it? Where are you going to put this ground? The safest place to put a ground to make sure that the magnetism or any fields that are built up inside of this part is right in the middle, and then weld towards it. So if I've got a ground that's sitting just like that, and I always weld towards it, it's always going to be the safest place. Because we're welding towards it, this condition of arc blow that we really see with stick welding, if you're a stick welder, you really know arc blow. Nothing teaches you more. But if I put it over here and I weld away from it, I'm going to get arc blow conditions. So welders move these grounds around all the time. We all have emery or a fine file that we can keep the surfaces clean. Because when we're welding and we hear that arc, we hear that ground go bad, we can watch our current drop, right? Constantly. And go, oh, that ground's done again. And then you go back and touch it, and you should be able to put your hand on it. If it's hot, there's a big problem. Big problem if it's hot. Should never get hot. And as I wrote down here too, I like deployment horizontally. I like that. I like it like this. Because all that spatter and stuff that can fall on top of this, that's going to give me all kinds of trouble, it's just going to fall straight down. Now, a couple of different options here. This little concept drawing from Welker is this fella right here. And Welker had this, or developed this for ground deployment. It's insulated, it's switched, and it has a flow control. Now, flow control is, under normal circumstances, well, why would I want to slow down the air to the cylinder and everything else? I will tell you this, there's one type of ground, and the ground is in there right now, that has 3 projections on it, one of them. And that particular one, you want to have that because it will hit so hard. Those projections will dig in so hard, it'll put 3 dents on every part. And that will not be acceptable. So I leave a flow restrictor on it. Now, this is very common. This is very new. And I'm thankful to have it because now I can deploy horizontally. I can lay it down like this and deploy horizontally. This is going to be my game changer for retrofit. Going forward, there's a lot of different things we can do, right, when we're putting it all in design. But for something that's already built, this is going to be fantastic because I can slip it right in and deploy a ground horizontally exactly the way I want it so it stays nice and clean. All kinds of advantages. Nice and tight. Switched. You can close. Yes. And most of the time we want it to happen fast. I just want to keep from dead. I put one on one time, and the guy just said, okay, the solenoid went bang, and it went pop, and put 3 dents. And the first 4 parts we made 3 beautiful dents. He goes, well, they're pretty tough. I said, yeah, they're tougher than your part. I think I better slow that down a little bit because I'm telling you right now, the customer won't like those dents. They're not going to accept it. So I always like switch. I always like to know, yes, you're fully deployed, or no, you're not. Flow control and insulated. You bolt that up to something, it's dead to the head. A little thing about insulation. Welding machines are getting sophisticated. Welding machines are getting sophisticated to the point where they all like their own ground if there's feedback. Now, I've seen it work and it's not, but some welding machines actually have a cable on them. There's a sensor. It's a voltage sensing lead. And what they do is they connect these up in various places, and every company's had their own, I don't want to tie one down, but they have their own method of where they want them affixed. Now, I've seen one of these, it wasn't this particular one, where they put 2 leads on it and put the sensor lead with it. And because there were 2 on one of these, it caused a major problem. The voltage chatter between the 2 caused a problem. We just simply went like this, put in a second one, and everything got fixed. Oh, they were talking about writing software to be able, well, hold on a second here. All you need is to make sure they're isolated for one. I said that you were talking about spending all kinds of money. Just make sure they're all deployed separately, right? And it's all better. I've seen up to 3 on that one type of ground. It was, it'd be a total of about 850 amps, something like that. Here's another. Yeah, I've seen 3 on it, to over 800 amps. It was one I couldn't wait to see. It wasn't getting hot. And the only reason it wasn't getting hot, there's a couple of reasons. First off, with this particular type of head, you're concentrating the force on the 3 little spots, so the force that was being added to it just kept the heat down. It was like putting a heavier spring on this. Right? It would also do the same thing for you. Providing we got a good surface, you could, right? But the chatter, oh man, when there were 2 of them welding together, you wouldn't have thought the parameters were ever close. And then one would stop and the other one would smooth right out. And it was very obvious, very quick what was going on with it. This is something else from Welker. There are cylinders, and there's different types. Now, this is what I'm going to go break into next, these different types of pads and surface contacts, because that's where the solution kind of comes from. So we've got different types of surfaces. It's just want to go over the surfaces for a second, because a lot of them, and what I consider to be probably the least efficient, is the knurled. We've all seen the knurled that look like it's got a knurled surface on it, and the idea is right. I get what people are saying. The idea is right because it's got points to it, and the points all hit. But how many points are hitting? Because it's knurled, it's always filled with dirt. As soon as it starts getting filled with dirt, you're done. That's when your problems really tie in. So these turn out to be fantastic, and they're probably all equal for the first time. The first time before they ever get used again. I would say, well, sure, maybe they're equal on the first time. Who knows? Because on this one, this is your knurled. I don't know how much surface area I have. I love math. I like to do math. I like math as a hobby. And what I like to do is I like to try to say that anything that I tell you that can actually work has got to be predictable mathematically. If I was to tell you how hard I'm pushing with this one, the knurled one, if I would say I'm pushing with this much force, I'm still not telling you what the concentration of pressure is because I don't know how much surface area I'm touching with. And the next batch of parts might be different again. So it's a constant challenge in that way. So the knurled ones, they're adaptable, they swivel, they try to find a spot, but depending on the stamping. The flat ones, these are the ones that there's tons and tons of the flat ones out there. Now the flat ones hold up very well. They service well. You can take a little buffer and you can buff the surfaces off. But if you take a flat one and you start at the start of a shift and check your micro-ohm reading at the end of the shift, you're going to know you've lost something because they get dirty, they get covered with stuff, they have all kinds of problems. Because we don't know, again, it's swivel on a stamped surface. What's good? What's the angle? How is it, do we have all the pressure we need on all the points? I don't even know how much I'm touching with here. But these work. And I would always say that this is probably the second best that you can do is to have something like this, but you've got to have a strong maintenance program. Okay, that's where my wheels fell off the wagon, because the strong maintenance program probably isn't going to happen. So I was faced with trying to figure out what to do and came up with our projection ground based on all the challenges above. How do I concentrate my force? Right? I don't want to take that engine cradle and push that engine cradle right out, like trying to push on it really hard with one of these. If I concentrate my force, I can mount it from underneath and I can push. Mathematically, I can figure out for a third of the pushing force, I can be pushing against the bottom of this thing because the pressure is concentrated into these 3 points. If you want to toss that around, you can. You might have seen one before. All right? So what we're trying to do is we're trying to concentrate our focus of pressure, which will help to create a better surface of conductivity. So there's a projection ground, the 3 points of contact on a stamping. Now it doesn't matter what I end up doing with it. It doesn't matter if the parts were stamped a little bit different, it would swivel to help us out. Now that particular one has a little rubber boot on it. See the rubber boot? That's very new. What I figured out was when that little, there's a little bit of copper grease in those. And that little bit of copper grease, when that copper grease dries out, it's actually becoming a little bit of a resistor. My micro-ohm was saying, oh, geez, something went out. I need to keep that grease there and fresh and clean. And I found out that if I sealed it up with some rubber and put a little O-ring there, a little snap ring to hold it forward, it was actually keeping everything clean, but it was also keeping the head from falling down in horizontal applications. I fixed a whole bunch of problems with just this little piece of rubber. And so this is going to be what the model that's going to be released in that condition. And there's one that worked for about 8 weeks. That was actually on 660 LX. And it was there for about 8 weeks. And then, I have to tell you this. This particular company used a spring. They just had a bit of a spring. Now, before we put these on, we put them on and everything was good. We made sure everything was lubricated and clean, but one of them failed. One of them stopped moving. It stopped as free, and so it couldn't apply the pressure was required, and it just drilled a hole right through the part. Exactly what you would expect it to do because we didn't have control over the force. So I tell everybody, unless I have the proper deployment, unless I have a way of getting it there, verifying it's there, verifying the force, all those things, that this is not the one for you. You could get by fine with those flat ones. You're still gonna have arcing, you're still gonna have problems, but this optimized the whole thing. Here's the best part about that one with the bumps. You mount it like that, the dirt falls on it, the spatter falls on it, it's not gonna fall right on all those 3 of those points. So it runs away. So it never gets a chance to accumulate for the next part to come up and hammer on top of it, hammer more of that spatter into the copper. That's actually it.